Hi everyone, welcome to Go Classes. In this session, we are going to discuss the practice set 2 of Combinatorics. In this practice set 2, we have recurrence relation questions from Kenneth Rosen. All the gate relevant standard questions I have taken in this practice set. Okay, so did you try this practice set? Did you try? I think there are 17 or 18 questions are there in this practice set. Did you try these questions? We are going to discuss all these questions in detailed way. We will discuss. Okay, and let me tell you one more thing. Before you see this session, before you watch this session, you should watch the complete recurrence relation playlist on the Go Classes YouTube channel. Okay, so on the Go Classes YouTube channel, complete recurrence relation playlist is available. Before you watch this session, okay, this video, before you watch this complete recurrence relation playlist you watch. Okay, the link I will put in the description. Okay, so very simple. Now let's start with the first question. So let's start with this question. Just give me a second. Okay, so let's start with this question. This is GATE Computer Science 2014 question on recurrence relation. So let's see. We will see multiple ways to solve this question. So let's start. So the question is saying that a pennant, okay, this new word is defined. A pennant is a sequence of numbers, each number being 1 or 2. N pennant means a sequence of numbers with summation equal to n. For example, this is a 4 pennant because the summation equal to 4. Okay. Next, the set of all 1 pennant, that is only 1, because remember you can only use 1, 2. Okay, very simple. Sequence of 1, 2. Sequence of 1, 2. You can only use 1, 2. N pennant means summation must be equal to n. Okay, so for example, the set of all 2 pennants, that is, this is a 2 pennant and this is a 2 pennant. Similarly, the set of all 3 pennants, this is a 3 pennant, summation equal to 3, summation equal to 3, summation equal to 3. And the question is saying that order matters, because you can see this is not same as this. Okay, the summation equal to 3, here 1, 2, this is a 3 pennant, this is a 3 pennant, and similarly this 2, 1, this is also a 3 pennant, and they are different, so order matters. The question is asking the number of 10 pennants. Okay, so this is a very simple question. Let's solve it. First of all, you understand this question, then you solve this question. First of all, the question is saying that what are the 3 pennants? What are the 3 pennants? Okay, so let's see what are the 3 pennants. 3 pennants means you can only use 1, 2, sequence of 1, 2, where summation equal to 3. Remember this point. 3 pennant, what is that? That is sequence of 1, 2, where summation equal to 3. And I can say, what is n pennant? What is n pennant? N pennant is sequence. In a sequence, order matters. Remember, in a sequence, order matters. This is given in the question that order matters. So this is a sequence of 1, 2. You can only use 1, 2. This is a sequence of 1, 2, such that summation equal to 3. Okay, such that summation is equal to n. Summation is equal to n. Very simple. So what is 3 pennant? For example, you can see you can only use 1, 2, sequence of 1, 2, where summation equal to 3. So I can say that this 2, 1, this is a pennant. Similarly, 1, 2, this is a pennant. And similarly, 1, 1, this is a pennant. You can only use 1, 2. Remember, you cannot use this because you cannot use 3. Okay, very simple. Okay, remember this point. You can only use 1, 2, sequence of 1, 2, where summation equal to n. This is n pennant. Okay, in the sequence order matters. This is given in the question that 1, 2 is different from 2, 1. Okay, now let's see. The question is asking the number of 10 pennants. So before that, let's find out number of 5 pennants or maybe 4 pennants. Let's see. Let's find out number of 4 pennants. Okay, so what is the number of 4 pennants? So let's see the method number 1. Okay, we will find the number of 4 pennants, but okay, to find this, let's see method number 1. What is the method number 1? See, method number 1 is very simple. You don't have to do much. You know that 4 pennant means sequence of 1, 2, where summation will be equal to 4. So what you can do, you can create cases. You can create cases. Cases you can create. For example, you can create this case that you will use 4 times 1, means you will not use 2. Okay, remember you can use 1 comma 2, and case 1 means you will not use 2. You will not use 2. Okay, next, what is case 2? What is case 2? Case 2 means you will use 1, you will use 2. Okay, you will use 2. So you can notice, if you use 1 times 2, okay, here you can, here you are not using 2, or I can say number of 2s that we are using, that is 0. Okay, here we are not using any 2. Here we are using 1 2. This 2 we are using. Okay, you can see the summation equal to 4. And what is the case number? What is the case number 3? We can use 2 2. Okay, we can use 2 2. Agree? Yes or no? Now you tell me one thing. Here how many ways? What is the number of ways here? If you do not use any 2, if you do not use any 2, all are 1, then only one way, only one way. So what you can do, you can create only one pennant. Okay, you can only create 1 4 pennant you can create. Okay, so the number of 4 pennants, or I can say number of ways means the number of 4 pennants. How many 4 pennants are there? So the number of 4 pennants. So you tell me here how many 4 pennants you can create. You can create any permutation of these, because the order matters. Yes or no? You can create any permutation of these, 1 1 2. You can create any permutation of these. So that is very simple. 3 factorial divided by 2 factorial. Okay, this is very simple to that. For example, if I ask you how many permutations of AAB, what will be the answer? For this, how many permutations will be there? How many permutations you can create for AAB? That will be 3 factorial divided by 2 factorial. We already know. So similarly here, how many permutation you can create? That will be 3 factorial divided by 2 factorial. Okay, next, what is the answer for this? How many permutation you can create? 2 factorial divided by 2 factorial. That will be 2 factorial divided by 2 factorial. For example, if I ask you for this BB, how many permutations you can create? How many permutations you can create? So that will be 2 factorial divided by 2 factorial, because they are same. So 2 factorial. Okay, so very simple. Now you can see here answer will be here 1, and this 3 factorial divided by 2 factorial, that will be 3, and this will be 1. Total answer is what? What is total answer? That will be 4. So how many 4 pennants you can create? So the number of 4 pennants, that will be equal to 4. So very simple. You can create total 4 pennants. You can 4 pennants you can create. So remember, number of 4 pennants. What is that? That is equal to 4. And which are these 4 pennants? For example, you can create this 4 pennant. You can use 1 2. Okay, you can create this. You can create this. You can create this, and also you can create 2 comma 2. So you can easily notice. Sorry, total how many? 5. Okay, summation equal to 5. Sorry, 3 plus 2, that is equal to 5. So total how many 4 pennants you can create? That will be 5. Total 4 pennants we can create. Okay, so very simple. Is this point clear? This is method number 1. Okay, very simple. Method number 1 is very simple, right? So tell me, if I ask you how many 10 pennants you can create, the question is asking 10 pennants. How many 10 pennants you can create? This is the question. So tell me, how will you do? Okay, what you can do? You can use your method number 1. Again, very simple method. Okay, just create cases, nothing else. Very simple method. What you can do? You want to find 10 pennants. 10 pennants means summation equal to 10. Sequence of 1 comma 2. Okay, remember 10 pennant means sequence of 1 comma 2 with summation 10. Okay, the summation should be equal to 10. So what you can do? You can create cases. You can decide how many 2s you are going to use. Okay, so what you can decide? You can decide how many 2s you are going to use. So what you can do? You can create case 1. In case 1, you are using no 2. Okay, you are using no 2. If you are using no 2, it simply means all the ones you are using. It simply means you are using all the ones. Okay, 5, 1, 2, 3, 4, 5. Okay, so you are using all the ones. Is this point clear? So if you are using no 2, okay, in the case number 1, I am not going to use 2. This 2 I am not going to use. Means sequence of 1. Sequence of 1. Summation should be equal to 10. Summation should be equal to 10. Okay, this is summation. This summation should be equal to 10. So how many ways are there? Means how many 10 pennants you can create in this way? In this way, how many 10 pennants you can create? Only 1. Okay, this is the only 1 10 pennant you can create. You are using all the ones. Okay, so you can only, this is only 1. Okay, in this case. What about case 2? Tell me, what about case 2? You are going to use 1 2. You are going to use 1 2. means you are going to use 1, 2. It simply means how many ones you will use. If you use 1, 2, then how many ones you need to use? Total 8, right? Total 8. So very simple. Now any permutation, because order matters. Agree? You can create any permutation. Remember, in a sequence, order matters. So you can create any permutation. Every permutation will be a pennant. Every permutation will be a 10 pennant. So how many permutations are there? Here you can notice these are same. It's like 8 times A and 1 time B. This is like this. 8 times A. It's like 8 times A, then A, and then B. So how many permutations are there? Tell me. What is the number of permutations here? So the number of permutations will be 9 factorial divided by 8 factorial. Agree? Very simple. Total 9 factorial. How many permutations are there? That will be 9 factorial divided by 8 factorial. So very simple. The same thing here. Any permutation you can create. So it will be 9 factorial divided by 8 factorial. That is equal to 9. Okay. What is the case number 3? What is the case number 3? You can use 2 twos. If you are using 2 twos, how many ones you need to use? Remember, the summation should be equal to 10. So if you are using 2 twos, then how many ones you are going to use? A total 6 ones. 6 ones and 2 twos. Now, any permutation here, you can create any permutation because order matters. Okay, in a sequence, order matters. In the pennant, when you create the pennant, then order matters. So tell me how many? Like, for example, if you have 6 A's and 2 B's. So how many permutations are there? What is the number of permutations? Tell me. Tell me the answer. That will be total how many? Total you have 8 factorial divided by 6 factorial, 2 factorial. Divided by 6 factorial, 2 factorial. Okay, very simple. Yes or no? Because these are 6. You have 6 A's, you have 6 A's, and you have 2 B's. So very simple. Total will be 8 factorial divided by 6 factorial, 2 factorial. This will be your answer in this case. So in this case, you will have 8 factorial divided by 6 factorial, 2 factorial. You can check it out, whatever this value is. Can you tell me? Can anyone tell me what is this value? So you can see it will be 8 into 7 divided by 2. So I think it will be 24. You can check it out. Okay. Next, what is the case number 4? Tell me, what is the case number 4? In case number 4, you can use 3 twos, right? You can use total 3 twos. So total 3 twos you can use. If you are using 3 twos, then how many ones you are using? Tell me. Number of 10 pennants we want. So tell me how many ones you are using. If you are using 3 twos, it simply means you are using 4 ones and 3 twos. Okay, 4 ones, 3 twos. Now in this situation, your answer will be what? That will be 7 factorial divided by 4 factorial, 3 factorial. So it will be 7 factorial divided by 4 factorial, 3 factorial. Next, what is the case number 5? What is the case number 5? That is, you are using 4 twos. You are using 4 twos. If you are using 4 twos, then how many ones you are using? You are using 4 twos. So it means only 2 ones you are using. Now the answer will be what? Any permutation. You create any permutation here. So how many 10 pennants you can create where you are using 4 twos? So that will be your 6 factorial divided by 2 factorial, 4 factorial. So it will be 6 factorial divided by 2 factorial, 4 factorial. And finally, what the case number 6? The case number 6 is you are using all the 5 twos. You are using all the 5 twos. So that will be like 2, 2, 2, 2, 2. You are using all the 5 twos. If you are using all the 5 twos, then there is only one way, or you can do like this: 5 factorial divided by 5 factorial. See, either you can say only one, because only one way, all twos you are using, all twos. So, or what you can do, you can create any permutation. Any permutation means 5 factorial divided by, because all are same, so 5 factorial divided by 5 factorial. Anyway, you will get 1. So you calculate this one. What will be this? Please tell me here what will be the answer. I think it will be 35. Okay, it will be 35. And what will be the answer here? So this will be, I think it will be 15. Now you tell me the total. What is the total number of 10 pennants that we got? So what is the total number of 10 pennants? So the number of 10 pennants, what we got, that you can just add all of them. 1 plus 9 plus 24, 1 plus 9 plus 24 plus 35 plus 15 plus 1 plus 35 plus 15 plus 1. Okay, you can check. What is this value? Can anyone tell me? Okay, you just calculate this value, you will get your answer. Okay, very simple, isn't it? So this is your method number one. We have seen method number one only. This is the method number one for solving this question. Did you understand this? Please tell me. Did you understand this method? Okay, is there any mistake here? So in the calculation, here you will get 8 into 7. Yeah, that will be 28. Okay, so this will not be 24, this will be 28. So if this is 28, then it will be 28. Okay, you can add all of them. What will be the answer? Is the answer 85? 85 or 89? Tell me. What the answer? You can check it. Okay, you can do the summation. That will be your answer. 89. Very good. Okay, so tell me here. Did you understand this one? This question, did you understand? This method, did you understand? Method number one. We have seen the method number one to solve this question. Okay. Now let's see method number two also. So if you understood the method number one, then let's see method number two also. What is that? That is more interesting. That is, can you create recurrence relation for n pennant? See, very simple. Can you create a recurrence relation for n pennant? We know what is n pennant. If I want to create n pennant, then what I need? I want to create n pennant. Then this is nothing but a sequence. It is a sequence of 1, 2, right? It is a sequence of 1, 2 with the summation equal to n. The summation should be equal to n. Okay, with the summation equal to n. So, and in this order matters, right? This is already given in the question, that order matters. In which order you do, that matters. Okay, so can you create a recurrence relation for this? Now this is our method number two. Our method number two for solving this question, what is that? That is, can you create a recurrence relation? Okay, let's create a recurrence relation for this. You tell me one thing. Here order matters, right? So what I put on the first position, that matters or not? Tell me. Simple question I am asking. What I put in the first position, that matters or not? For example, order matters. So what I put in the first position, that matters, correct? Okay. In the first position, what are the choices? I want to create a recurrence relation for n pennant. N pennant means this is a sequence of 1, 2. I can only use 1, 2. And the summation should be equal to n. The summation must be equal to n. Okay. So the summation should be equal to n. And the order matters. So what I put here, that matters, correct? For example, if I put 1 here, can I say that will be different if I put 2 here? If I put 1 here, can I say? Because order matters. Okay, so very simple. Here I can say this and this, they are different. This and this, they are different, right? So either you can put 1 here or you can put 2 here. Only two choices you have. Either you can do this or you can do this. There is no other choice because we can only use 1, 2. Now you tell me, I want how many n pennants I can create. So let's assume number of n pennants is equal to fn. So let's assume number of n pennants. I'm saying that number of. So let's assume number of n pennants, and that is equal to f of n. Let's assume. Okay, that is number of n pennants. So you tell me, if I want to create n pennants, just focus on n pennants. If I want to create n pennants, then there are two ways. What I can do, either I can start with 1. Or what I can do, I can start with 2. Either I can start with 1 or I can start with 2. Now, if I am starting with 1, in this case, how many n pennants are there? If I am starting with 1, this is fixed. I am starting with 1. Okay, in this case, how many n pennants are there? In this case, so if I am starting with 1, I want the summation equal to n. The total summation should be equal to n. So tell me what summation I want here. I want n minus 1. Very simple. Agree or not? See, the total summation I want, this total summation should be equal to n. Now, if I start with 1, then here I want n minus 1. Correct? So what I want here, I want n minus 1 pennant. So here I want n minus 1 pennant. Okay, so I can say number of n pennants, that will be equal to number of n minus 1 pennants. Okay, when you start with 1, then you can count number of n minus 1 pennants plus, or there is or here. Okay, there is or here. So plus, you can start with 2. If you start with 2, then what I want, tell me. If you start with 2, then what I want here, I want n minus 2 pennant. Because if I'm starting with 2, then the summation I want equal to n minus 2. I want summation equal to n minus 2. So what I can do, I can say number of n pennants that is equal to, if I start with 2, then I can count number of n minus 2 pennant. Okay, if I'm starting with 2, already this is fixed. This is fixed. I'm starting with 2. If I'm starting with 2, then I can count number of n minus 2 pennants. And if I'm starting with 1, I can count number of n minus 1 pennants. Okay, so very simple point, very simple. Remember, if I start with 2, I can count number of n minus 2 pennants. If I start with 1, I can count number of n minus 1 pennants. Either I can do this or I can do this, and these are mutually exclusive. These are mutually exclusive because here I am starting with 1, here I am starting with 2, so they are different. So this case and this case, they are mutually exclusive. So finally, my answer will be what? How many n pennants I can create? That will be equal to fn minus 1 plus fn minus 2. So very simple. The number of n pennants, that will be number of n minus 1 pennants plus number of n minus 2 pennants. This will be the recurrence relation. Okay, this is going to be the recurrence relation. And what are the base conditions? What are the initial conditions? Tell me. If I ask you what is f1, f1 means number of 1 pennants. How many? Number of 1 pennants. So how many? If I want number of 1 pennants, then that will be only 1. Okay, because what you can do, you can just simply do like this. This is the only. Okay, so that will be 1. Okay, and that is your, this is the only 1 pennant you can create. How many 2 pennants you can create? Number of 2 pennants. Tell me how many 2 pennants I can create. See, if I want to create 2 pennants, either I can do this, I can either do this, or what I can do, I can do this. So number of 2 pennants, that will be 2. That will be 2. These are the initial conditions. So I got initial conditions, I got recurrence relation. Now I can find anything. I know what is f1. Okay, I know what is f1. F1, that is equal to 1. What is f2? F2 is equal to 2. Okay, and I have this recurrence relation, that fn is equal to fn minus 1 plus fn minus 2. So tell me what will be f3? Tell me what will be f3? F3 will be equal to f1, f2 plus f1. F3 will be f2 plus f1. So what will be f3? F3 will be f2 plus f1. F2 plus f1. That will be 3. What will be f4? F4 will be f3 plus f2. So that will be 5. And what will be f5? F5 will be f4 plus f3. That will be 8. Okay, and what will be f6? For example, what will be f6? Remember, f6, that is equal to f5 plus f4. If I put n equal to 6, then I will get f6 equal to f5 plus f4. So that will be f5 plus f4. What is f5? That is 8. What is f4? That is 5. So that will be 13. So remember, f6, that will be 13. Similarly, I can find f7. That will be what? 13 plus 8. That will be 21. Okay, what about f8? Can you tell me what about f8? F8 will be summation of these two. That will be 34. What will be f9? F9 will be summation of this and this. What that will be? That will be 55. And finally, what is f10? F10 is summation of 55 plus 34. So that will be 89. So your final answer will be 89. Is this clear? This is your final answer. So we have seen 2 methods. Method number 1, method number 2. Tell me, which is your favorite method? Which method did you like? See, for this question, how to find n pennants? How to find 10 pennants? How to find 10 pennants? We have seen total 2 methods we have seen. We have seen method number 1 and we have seen method number 2. We have seen using recurrence relation also. Method number 2 means using recurrence relation. In this method number 2, we are creating the recurrence relation. And this recurrence relation, we are creating that number of n pennants is equal to number of n minus 1 pennants plus number of n minus 2 pennants. Okay, because number of n pennants, that is equal to, if you start with 1, then you can count number of n minus 1 pennants. If you start with 2, then you can count number of n minus 2 pennants. So this is the method number 2. This is the recurrence relation method. Recurrence relation method. Okay, and what is method number 1? That is your by case method. In this, you are creating the cases. You are creating the cases means how many 2s you are taking. Okay, you can take 0, 2, you can take 1, 2, 2, 2, 3, 2, and so on. So two methods we have seen to solve this question. Tell me, did you understand both of them? I want to ask you, did you understand both the methods? This method also, this method also. Did you understand both of them? Second point, which method did you like more? Which method did you like more? You can tell me. Okay. So anyway, this is your question. This is your GATE 2014 question. You can see GATE 2014 question. Very nice question. Now I can tell you one thing, that the question maker of this question, okay, the professor who has created this question, what do you think? Which method he is thinking? The professor who created this question, what method this professor is thinking that students will be using? Tell me, like this professor will be having which method in mind? Method 1 or method 2? I think method 2. Okay, because this is more, I can say, more analytical method. This method number 2, this is more analytical method. This is more, I can say, more sophisticated. Okay, method number 2, this is more sophisticated method. So anyway, but you have method number 1 also, you have method number 2 also. You can use any of them. But the most important point is not getting the answer. That is understanding the method. You understand this also, you understand this also. What many students do? Many students, what they will do? They will understand this method, they will get the answer, and they will not try to understand this. Okay, I have seen this. Okay, many students, what they will say? They will say, yes, I got this method. This method I understood. I got my answer. Now they will not care about this method. They will not try to understand this method. But you should understand everything. Okay, you should understand every method, everything you should understand. In the GATE exam, you can apply any method that you want. You can use this method or you can use this method. That is your choice. But understand everything. Okay, let's move on now. Now let's see this question. So this is Kenneth Rosen, exercise 8.1, question number 11, applications of recurrence relation. The question is asking, find a recurrence relation for number of ways to climb n stairs if person climbing the stairs can either take one stair or can take two stairs at a time. Okay, either you can take one stair at a time or you can take two stairs at a time. We need to find the recurrence relation. And also we need to find what is the initial condition. Also we need to find what is, if you want to, what is the number of ways to climb 8 stairs. So this is the question. Let's solve it. So the question is actually very simple. First, to tell me what are the initial conditions. Let's start with initial conditions. Remember, the question is saying that you can either use one stair, you can either take one stair, or you can take two stairs at a time. Okay, at a time, either you can take one stair, either you can go like this. Okay, either you can go like this. Means if you are here, either you can go here. So this is your one step. Okay, you are taking one step. Or what you can do, or you can do this. Or you can do this. If you are here, then you can do this. This is your two step. So either you can take one step or you can take two step. If you, for example, if you are tired, you can take one step. If you are energetic, then you can take two step. But the point is, at any point of time, at a time, you can either jump one step or you can take two step. Very simple. Okay. Now we need to see. Okay, let's see the initial conditions first. In this question, let's see the initial conditions. What are the initial conditions? For example, tell me, if you have only two stairs, then how many ways are there? If you have only two stairs, for example, let's assume this is the stair and then this is the stair. Okay, so tell me how many ways are there if you have two stairs? Let's assume, one more thing I want to tell you. So just give me a second. I want to tell you, let's assume that Fn, what is Fn? That is number of ways to, I can say, or maybe you can say Sn. What is Sn? That is number of ways to climb n stairs. To climb n stairs. Okay, so Sn, what is that Sn? That is number of ways to climb n stairs, taking one or two steps at a time. Okay, taking one or two steps at a time. Either you can take one step at a time or you can take two steps at a time, taking one or two steps at a time. This is your Sn. Okay, how to climb n stairs. This is Sn. So tell me, what will be S2? What will be S2? If you have two stairs, stair number 1, stair number 2, if you have two stairs, then either you can do like this. See, You can take one step, then you can take one step. Okay, if you have two stairs, then you can go 1, 1. So either you can go 1, 1, very simple. Either you can go like this 1, 1, or you can directly take two steps. See, either you can take 1, 1, or you can directly take two steps. So very simple. I can say that there are two ways. S2 will be equal to 2. There are two ways. Okay. Either you can take two steps directly, or you can take 1, 1. Okay. Either you can from here, for example, from here, either you can directly go here, or what you can do, you can go here, then you can go here. So very simple. Tell me what is S1? Means you have only one stair. Only one stair. If you have only one stair, then this is the only possibility. This is the only possibility. So the answer will be 1. S1 will be 1. Okay, let's see what is S3. Let's find out what is S3, so that we can understand the problem. Tell me what is S3. Means you have 3 stairs. So how to climb 3 stairs? What you can do? Either you can see, just decide. Either you can take 1, 1, 1. Okay. Or what you can do? You can take, first you can take one step, then you can take two step. Or first you can take two step, then you can take one step. So very simple, right? Okay. So this is your S3. So remember S3 will be equal to 3. So this S3, this is equal to 3. S3 equal to 3. Because these are the ways. Now let's see. Let's solve this problem for n steps. So I'm again telling you method number 1. We want recurrence relation. The question is asking for recurrence relation. So I will tell you recurrence relation, but recurrence relation you can create using two ways. Let me tell you something interesting. If you are creating recurrence relation, if you are creating recursive equation, if you are recursively solving a problem, then there are two ways. If you are creating recurrence relation, remember this point. If you are recursively solving a problem, then there are two ways. What are the two ways? See, either you can do something in the beginning and then let the recursion do everything. Agree with me? What you can do, there are two ways. If you want to create recursive relation, if you want to create, if you are solving a problem recursively, then what you can do, there are two ways. What you can do, in the beginning you can do some work and then you can apply the recursion. Agree? Is this point clear? In the beginning you do some work, means you do some work. Here you do some work, you do. Okay, just do some work. And then what you do, then let the recursion handle everything. Agree? Let the recursion handle everything. Is this point clear? Please tell me. What you can do, you can do some work in the beginning, then you can apply the recursion. Okay, then you can apply the recursion. Or what you can do, you can apply the recursion, and you can do some work in the end. Agree with me? You can apply the recursion and at the end you can do some work. Here you can do some work. Please tell me, is this point clear? See, there are two ways to recursively solve a problem. If you want to solve a problem recursively, then what you can do, there are two ways. Either in the beginning you do some work and then you apply the recursion. Or what you can do, you can apply the recursion and then at the end you can do some work. Did you understand these two? Please tell me. Did you understand? Now let's see with example. In this question, I am going to apply this method. So method number 1, in the beginning, I will do some work. Okay, I will do some work in the beginning and then at the end, I will apply the recursion. In the method number 1, what I will do, in the beginning, some work I will do. I will do some work. And then I will apply the recursion. Okay, and then I will apply the recursion. Is this point clear? Then I will apply the recursion. This is the method number 1. In the beginning, some work I will do, then I will apply the recursion. So tell me, in the beginning, what are the work I can do? Means you have n stairs. So in the beginning, what I can do? In the beginning, either I can take one step, means when I am taking, like in the beginning, how many steps I can take? Tell me. In the beginning, how many steps I can take? Just tell me simple point. In the beginning, okay, in the beginning, how many steps I can take? Means I'm creating like this. So in the beginning, how many steps I can take? Either I can climb one stair. Okay, either I can climb one stair in the beginning, or what I can do, I can climb two stairs in the beginning. Either I can climb one stair in the beginning, okay, or I can climb two stairs in the beginning. Okay, either I can start with one step or I can start with two steps. Now you tell me, how many ways are there? This Sn, this is number of ways to climb n stairs. Okay, how many ways to climb n stairs? So tell me, this Sn will be equal to, if I start with 1, then now I need to climb n minus 1 stairs, right? Yes or no? If I start with 1 step, now I need to climb. How many steps I need to climb? I need to climb total n minus 1 steps. Okay, these n minus 1 steps I need to climb. So remember, number of ways to climb n steps, n stairs, number of ways to climb n stairs, that will be equal to, if I start with 1, then I can count number of ways to climb n minus 1 stairs, or because of this I am getting this, or what I can do, if I start with 2 steps, in the beginning if I take 2 steps, then what I need to do after this, what I need to do, if I start with the 2 steps, then what I need to do, I need to climb n minus 2 stairs. I need to climb n minus 2. These are the n minus 2 stairs, and here you have n minus 1 stairs. So if I start with the 2 steps, then I need to climb n minus 2 stairs. So that will be, I can say, Sn minus 2. Okay, so this is your idea. This is the idea number 1. So in the idea number 1, in the method number 1, what I'm doing, can you see what I'm doing? In the beginning, I'm doing some work. Either I can start with 1 step, or I can start with the 2 step. Then I'm applying the recursion. Agree with me? Do you agree with me that in the beginning I'm doing some work? Either I can take 1 step, or I can take 2 step. In the beginning, 1 step or 2 step I can take. Okay. After that, I'm applying the recursion. So very simple here. In the beginning, if I take 1 step, then I need to climb n minus 1 stairs. In the beginning, if I take 2 steps, then I need to climb n minus 2 stairs. So this is the method number 1. Okay, you got this recurrence relation. What is the method number 2? What is the method number 2? Tell me. In the method number 2, what you will do? In the method number 2, you will apply the recursion. Okay, you will apply the recursion. You will assume that recursion has already happened. You will assume that recursion has already happened. You will assume that already everything is done. Everything is already done. You just need to take care of the last step. Okay, you just need to take care of the last step. Is this point clear? Please tell me. Okay, in the method number 2, you will assume that everything is already done. Everything is already done means you are already on the, you are already here. For example, if these are the stairs, then in the method number 2, you will assume that you are already here. Let's assume you are already here. Okay, so what you will assume in the method number 2, you will assume recursion has already happened. Now you just need to do some work at the end. Some work at the end. This is like, I can say, some final work. I can say the last work. Okay, I can say this is the last work. I can call it last work, final work. Okay, very simple. I hope this point is clear. So tell me, if you have already, what your last work can be. Just tell me what your last work can be. Your final work, your last work. Just tell me the last work. Either your last work can be 1 step. Either you can take 1 step, or you can take 2 step. Agree? Agree with me? See, your last work. Just tell me what is your last work. Your last work can be either 1 step, or it can be 2 step. This is your last work. Okay, if you are doing this last work, means how many steps you have already climbed? If you are doing this last work, if this is your last work, this is the final last work, it means how many stairs you have already climbed? N minus 1. Yes or no? See, if this is your last work, then it means you have already climbed n minus 1 stairs. You have already climbed n minus 1 stairs, and you just need to climb 1 step. Okay, you just need to take 1 step. Or what you can do, if this is your last work, then tell me what you have already done. If this is your last work, then how many stairs you have already climbed? Tell me. That is equal to Sn minus 2. That is n minus 2, right? That is n minus 2. So I can simply say that your recurrence relation will be like this. So both the methods, did you understand? See, very simple point I'm telling you. There are 2 methods. There is method number 1 for writing recurrence relation. There is method number 2 for writing recurrence relation. Method number 1 is like this. You do first work. And then you apply the recursion. Okay, you do some work in the beginning, and then you can apply the recursion. Is this point clear? You can do the first work. Initially, in the beginning, you can do some work, and then you can apply the recursion. Then recursion will handle everything. Okay, or what you can do, or what is method number 2? In the method number 2, let's assume recursion has already done. Recursion has already handled everything. This recursion has already handled everything. You just need to do some last work. You just need to do some last work. I hope this point is clear. Interesting, right? So there are two ways. Method number 1 for writing recurrence relation. Here also you are writing recurrence relation. In the method number 1 also you are writing the recurrence relation. And here also you are writing the recurrence relation. But there are two ways. In the method number 1, you can assume that I will do some work in the beginning and then recursion will handle everything. In the method number 2, let's assume recursion has already handled everything. Recursion is already over. Now I need to do some last work. So these are the two methods. And we have seen both of them. Okay, in the method number 2, your answer will be, your recurrence relation will be this, and same recurrence relation you will get in method number 1. So whether you apply method number 1 or you apply method number 2, that is your choice. Ultimately, what is Sn? Sn means how many ways to climb n stairs. That is equal to Sn minus 1 plus Sn minus 2. If I start with 1 step, then Sn minus 1. If I start with 2 step, then Sn minus 2. Okay. So very simple. This is your recurrence relation. And you already know the initial conditions. Your initial condition S1 is 1 and S2 is equal to 3. Sorry, S2 equal to 2. Okay, so these are the initial conditions. Now you can easily find what is S3. So S3 will be equal to what? S3. If I put n equal to 3, then that will be equal to S3 equal to S2 plus S1. So that will be equal to S2 plus S1. Okay, and that is 3. What is S4? What is S4? That is S3. That is S3 plus S2. That will be 5. What is S5? That will be S4 plus S3. That will be 8. What is S6? That will be S5 plus S4. That will be 13, and so on. You can, like this, you can count. Okay, you can do it. Okay, you can do it. The question is asking S8. What is S7? S7 is summation of these two. That will be 21. And what is S8? That will be summation of 21 plus 13. That will be 34. So how many ways to climb 8 stairs? How many ways to climb 8 stairs? That will be 34. This is your answer. Now, let me tell you one thing. Let me tell you, that is, see, I told you two methods for writing recurrence relation. Agree? Writing recurrence relation. Whenever you are writing recurrence relation, then I told you two methods. If you are writing the recurrence relation, I told you there are two methods. Either you can use method number 1 or you can use method number 2. Okay. In the method number 1, remember, this is actually important. In the method number 1, what you can do? You can do some work in the beginning. In the beginning, some work you will do, or I can say it's like you will do some first work. Some work you will do in the beginning, then the recursion will happen. Then the recursion will start. Okay, you do some work in the beginning, then recursion will start. In the method number 2, the recursion will happen. The recursion will happen, and then you will do some work. Then you will do some last work, I can say. Okay, you will handle the last work. So here you are handling the first work, and here you are handling the last work. Okay, in this method number 1, you handle the first work, and recursion will handle the remaining. In the method number 2, recursion will handle the initial part, and you will handle the last work. You only have to handle the last work, and the recursion will handle the remaining. So I told you two methods. Let me tell you one thing. In some questions, method number 2 you will apply. In some questions, method number 1 you can apply. In some questions, both of them you can apply. Is this point clear? Please tell me. In some questions, in some problems, method number 1 you can apply. In some problems, method number 2 you can apply. And in some problems, you can apply both of them. In the previous problem, when you are climbing the stairs, you can apply both of them, right? You can apply method number 1 also, method number 2 also. Agree? But let me tell you, there are some questions, there are some problems where only this method you can apply. You cannot apply this. In some problems, only this you can apply. You cannot apply this. I hope this point is clear. Please tell me. So that is the reason I am telling you two methods. Okay, but both are very similar to each other. But in some problems, this will be useful. This will not be useful. In some problems, this will be useful. This will not be useful. In some problems, both of them are useful. Okay, let's move on. So let's see this question. Kenneth Rosen, exercise 8.1, question number 12. Now we need to, this question is saying that find a recurrence relation for the number of ways to climb n stairs if the person climbing the stairs can take 1 or 2 or 3 stairs at a time. So what your answer will be? Now what you are doing, remember, in this question what you are doing, either you can take 1 or you can take 2 or you can take 3 steps at a time. Okay, so tell me, what is Sn? Sn is number of ways, Sn, that is number of ways to climb n stairs. To climb n stairs. To climb n stairs with either you can take 1 or 2 or 3 steps at a time. 3 steps at a time. Okay, so at a time, either you can take 1 step or you can take 2 steps or you can take 3 steps. These are the possibilities. So this is your Sn, that is the number of ways to climb n stairs. So tell me what your answer will be, what the recurrence relation will be. See, very simple. Can I start with taking 1 step? Can I start? Can I start? See, I want to count how many ways are there to climb n stairs. I want to count Sn. I want to count Sn. This is what I want to find. Means how many ways are there to climb n stairs? These are the n stairs. Okay. Can I start with 1 step? Yes. Or what I can do? Tell me. I can start with 2 steps. Or I can start with 2 steps. Or what I can do? Tell me. Or I can start with 3 steps. Okay. These are the possibilities. Agree? I can start with 1 step, or I can start with 2 steps, or I can start with 3 steps. These are the possibilities. Okay. Very simple. If I start with 1 step, then what is the remaining work? If I start with 1 step, I have already taken 1 step. This 1 step I have already taken. Now I can count how many ways to climb n-1 stairs. Now I need to climb n-1 stairs. So here I need to climb n-1 stairs. Plus, if I start with 2 steps, then I need to count how to climb n-2 stairs. And if I start with 3 steps, then I need to count how many ways to climb n-3 stairs. So this is your recurrence relation. Is this point clear? Very similar to the previous question. Very similar to the previous question. This is your recurrence relation. So remember, finally your recurrence relation will be Sn equal to Sn-1 plus Sn-2 plus Sn-3. This will be your recurrence relation. Okay, and let's find out the initial conditions. What are the initial conditions? What are the initial conditions? Tell me. If you have 1 step, if you have only 1 stair in your house, if you have only 1 stair, then you can climb it on only 1 way. There is only 1 way to climb. There is only 1 way to climb. There is only 1 way to climb. If you have 2 stairs, then how many ways to climb? Then there are 2 ways to climb. Either you can climb like this, or you can climb like this. If you have 3 stairs in your house, if you have 3 stairs, then how many ways? See, either you can climb like this, 1 1 1, or you can climb like this, 1 2, or you can climb like this, 2 1, or you can climb like this, 3. So this S3 will be 4. This S3 will be 4. I hope this point is clear. So these are the initial conditions. Now you can find S4. Tell me what your S4 will be. Remember, this is the recurrence relation, that Sn is equal to Sn-1 plus Sn-2 plus Sn-3. So tell me what will be S4. If I put n equal to 4, then it will be like, I can say it will be S3 plus S2 plus S1. Okay, S3 is 4, S2 is 2, and plus 1. That will be equal to 7. Okay, so very simple. I hope this point is clear. Now let's move on. Let's solve this question. This is GATE 1989 question on substring. We need to count the number of substrings. Okay, this is GATE 1989. So you can see how many substrings are there of all lengths inclusive can be created from a character string of length n, such that all the characters are distinct. In this character string, in this string of length, there is a string of length n. In this string, all the characters are different. Now we need to count how many substrings we can create. Very simple. This is the question. This is the GATE question. GATE Computer Science 1989 question. Let me tell you one thing. This same question has come in the GATE exam 3 times. You can see the same question has come in the GATE exam. This question came in 1989. The same question came in 1994. And the same question came in 1998. One question came in the GATE exam. How many times? Total 3 times. One question came in the GATE exam. Okay, same question, exactly same question. Okay, so let's count it. Now, we will solve this question by 2 methods. So let's start with the method number 1. So, method number 1. Remember what you need to do? You need to count the number of substrings. You have a string. Let's assume you have a string. You have a string W. In this string W, you have total n characters. You have total n characters, A1, A2, and so on. Total an minus 1, an. Okay, so total n characters you have in this. In this, you have total n characters, or I can say n symbols you have. And all of them are distinct. This is already given to you that AI is different from AJ. Okay, AI is different from AJ for all I comma j. Whatever I comma j, whenever, so I can say basically these are different. Means, for example, A1, A2, these are different. A2, A3 are different. A1, A3 are different, like this. So you can easily see that AI is different from AJ whenever I is different from J. Okay, so now you tell me, we need to create how many substrings we can create. So let's see the method number 1. So let me take one example so that we can easily understand. Let's assume this is your string A, B, C, D, or maybe A, B, C, D, E. Let's assume this is your string. Now let's count the number of substrings. Let's count the number of substrings. So tell me what you will do. Remember, substring means what? Substring means consecutive. Agree? Yes or no? Substring. This you already know. What is a substring? Substring means consecutive part of a string. For example, if this is your string W, then consecutive part of this, that will be your substring. So if you say, for example, this is U, then I will say U is substring of W. U is a substring of W. Okay, very simple. So remember, consecutive. This U must be a consecutive part of it. This must be a consecutive part of W. I hope this point is clear. This is very important, that it should be a consecutive part of W. This is the definition of substring. So for example, now tell me, I am writing on one side, I am writing the length of substring, and on other side, I am writing number of substrings. So you tell me, how many substrings of length 1 we have? In this string W, how many substrings of length 1 we have? We have total 5 substrings, because you see, this is length 1, or 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 this is length 1. It is already given that all the characters are distinct. It is already given. All the characters are different. So very simple, I can say length 1 substrings, there are 5. How many length 2 substring? This is length 2 substring, means AB. Okay, AB. Tell me one thing. Which is a substring in this question? In this W, which is a substring of W? Tell me, which is a substring of W? Can I say AB or BA? Or are they both of them? Which is a substring? Can I say, see, this is a substring, consecutive. So tell me, AB, BA, both of them are substring, can I say? Can I say both are substring? No, this is not a substring, this is a substring. Order should not change. You should not change the order. Okay, you should not change the order. This order you should not change. Okay, remember, this order you should not change. Consecutive and orders you should not change. So how many 2 length substrings we have? You can create this 2 length substring, or you can create this one, or you can create this one, or you can create this one. So total 4. Okay, total 4. What you can do? What are these 4? These 4 are like this. You can create AB, you can create BC, you can create CD, you can create DE. How many 3 length substrings are there? 3 length. So you can create ABC, you can create BCD, you can create CDE. Only 3. Okay, so there will be 3. What are these? These are like ABC, then you have BCD, and then you have CDE. Okay, how many 4 length substrings are there? 4 length substrings. You can create ABCD, you can create BCDE. Okay, so that will be 2. That will be 2. 4 length substrings. That will be 2. So next, how many 5 length substrings are there? This is the only 5 length substring. That will be ABCDE. Okay, so that will be 1. Now there is one more thing. There is a 0 length substring. How many 0 length substrings you can create? how many zero length substrings you can create? Zero length substring, empty string. This we study in the theory of computation. In the theory of computation, we study this. So remember, if this is your string, if your string W is, for example, AB, then how many substrings are there? How many substrings are there? Substrings, remember, substring can have length 0 to the length. Remember, the length is greater than or equal to 0. Substring has length greater than or equal to 0. So length 0 substring you can create, that is only one empty string. This is called empty string. This is called empty string. This we study in the theory of computation subject. Okay, this is called empty string. Empty string means this is zero length string. Okay, this is a zero length string. The length of this string is 0. This is just a special string. You can call it null string. This is a very, very, very special string. Okay, so very simple point. Zero length string, that is one. Only one zero length string we have. This is one length string. This is one length string. This is two length substring. So very simple. Okay, now here also I can say how many zero length substrings are there? That will be one. So final answer will be what? See, the final answer will be this. You can add all of them. You can add all of them and plus one. So your final answer will be what? Your final answer will be how many for this string W equal to A, B, C, D, E. For this string, the number of substrings. The number of substrings. You are getting a very nice sequence. You are getting 1 to 5 you need to add. You need to add 1 to 5. Okay, 1 to 5 you need to add. Very simple. You just need to add 1 to 5. And this one is for empty string. This is for zero length string. This is for zero length string. There is only one zero length string. There is only one zero length string. Okay, so your answer will be, you can just add all of them and you can add one for zero length string. This is one more. Okay, so you can do that. Now let me tell you, if you have n characters, then what you will do? If you have n characters, all are different characters. AI is not equal to AJ. All of them are distinct. These are distinct characters. Now in this situation, let's count. Okay, on one side I am writing the length. On one side I am writing the length of substring. Okay, on the other side I am writing number of substrings. So tell me, if I ask you, how many substrings of length n are there? How many substrings of length n? How many substrings of length? That is length n. That is only one. How many substrings of length n? That is only one. Only one. This is the only one. How many substrings? Or maybe I can start with length 1. Okay. How many substrings of length 1? How many substrings of length 1? See, this is substring of length 1. 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 So that will be n. Because all the characters are different. This is already given in the question. All the characters are different. All these characters are different. A1, A2, these are different. A2, A3, these are different. A1, AN, these are different. So all these characters are different. Next, how many substrings of length 2? You can create this substring of length 2, this substring of length 2, A3, A4, and so on like this. So total how many? N minus 1 you can create. Okay, tell me how many substrings of length 3? You can create A1, A2, A3. You can create A2, A3, A4. You can create A3, A4, A5, and so on. So like this, if you see, you can create N minus 2 substrings. Okay, how many substrings of length 4? That will be N minus 3, and so on. How many substrings of length N? How many substrings of length N? That will be 1. Okay, that will be 1. That is going to be 1. Okay, and there is a one special substring, right? Yes or no? There is a special substring of length 0. Length 0 substring, that will be only 1. This is a special substring of length 0. Okay, this is your null string. Anyway, your answer will be what? See, you can add all of them. So I can say number of substring will be equal to number of substrings, that will be equal to 1 plus 2 plus and so on. Okay, till n. So till n. So that will be equal to what? That will be n plus 1 by 2. Okay, that will be n plus 1 by 2. And remember, there is one more. There is one more for null string. There is one more for null string. So this will be your answer. So you can add all of them. That will be n plus 1 by 2. And this is additional. This is one more. So that will be your plus 1. This is your answer. Is this point clear? Please tell me. So for this question, the answer will be this. Now let me tell you another method to solve this question. Let's see another method to solve this question. The same question we can solve by a different method. Can you create recurrence relation? See the method number 2. The method number 2 is recurrence relation method. Recurrence relation. Can you create a recurrence relation for number of substrings of length n? So let's assume you have a string that is a1, a2, a3, and so on an. Okay. Now let me say what is fn? Fn is number of substrings of length n. Okay, number of substrings of w. Okay, number of substrings of w. So fn, that is a number of substrings of w. Very simple. This is your fn, number of substrings of w, where w has length n. You already know w has length n. This w has length n. Okay, so very simple. I am saying that this fn is number of substrings of length w. You tell me one thing, a simple question I am asking. If you already have, for example, let me give you this string a, b, c, d. Let me give you this string, and you already know how many substrings are there. Means using this string, okay, let's assume you know that these many substrings you can create. Okay, let's assume I don't know what is this value. I do not know what is this value. I am saying that using from this string, let's assume these many substrings you can create. Okay, these many substrings you can create. Are you getting my point? I am saying that this is your string. For this string, how many substrings are there? How many substrings you can create? For this, how many substrings you can create? Let's assume that is f4 because the length is 4. Let's assume that is f4. I don't know what is the value of f4. Now I'm simply asking that if I add one more symbol, then I'm just asking how many additional strings will be there. Means you already have a, b, c, d. You have already counted using this how many substrings are there. See, please understand. Using this, how many substrings you can create, that is f4, that you have already counted. Now, if I add one more symbol, now how many new substrings will be there? You just tell me, this is the point. How many new substrings will be there? This f5, this will be equal to what? See, tell me, these will be already there. Agree with me? Means using this, how many substrings you created, that you will count or not? Please tell me. Using these 4 symbols, how many substrings you created, that you will count or not? Of course, that you will count. So that will be like f4 plus. How many new? Because of this new customer, because of this new character, how many new are there? Including this, you need to include this. Please tell me. For example, is this already counted CD? Is this already counted? Did I count this CD? Where did I count? This CD, where did I count? I have already counted in F4. This CD is already counted in F4. Did I count this ABC? Did I count this ABC? Yes, that is also counted in F4. This is also counted in F4. This is also counted in F4. This is also counted in F4. Okay, is this counted in F4? Is this counted in F4? This is counted in F4? No. Is this counted in F4? No. Is this counted in F4? No. So these are not counted. So how many new are there? See, you can create this new you can create. Okay, so or you can create this new, or you can create this new, or you can create this new, or you can create this new. Total how many new you created? Total 5 new you created. Yes or no? Because of this E, how many new are there? See, this new is there, this new is there, this new, and this new. Total, these 5 new you got. Is this point clear? Okay, did I count empty string? Where is empty string counted? Tell me, where is 0 length string counted? Where did I count 0 length string? That is already counted in F4. That is already counted in F4. Okay, because using these characters, using these 4 characters, every substring is already counted here. Using these 4 characters, every substring I have already counted in F4. Now, new will be, because of this character, new will be total 5. Okay, because this is the new, this is the new, this is the new, this is the new, and finally this is the new. I hope this point is clear. So tell me, can you write this? Can you write the recurrence relation now? Now can you write the recurrence relation? So very simple. Using these characters a1, a2, an minus 1. Using these characters, let's assume that substrings are fn minus 1. Let's assume substrings are fn minus 1. Let's assume. Now you tell me, using these characters, I'm saying that using these characters a1 to an minus 1, a1 to an minus 1, a1 to an minus 1, these many substrings are there. These many, using these characters, these many substrings are there. Now for this new, for this one, how many new will be there? If I add this an, if I add this an, now how many substrings, new substrings will be there? So here you tell me what will be fn? That will be fn minus 1 plus fn minus 1 plus new substrings. How many new substrings? Because of this character, total n new substrings will be there. These will be the new. So this is your recurrence relation. Isn't it interesting? Are you finding recurrence relation concept interesting? Recurrence relation, when you are writing recurrence relation, you will always find these things are interesting. These are not boring. Okay, writing recurrence relation is always interesting. You will find it very interesting. So tell me, did you understand this recurrence relation? So finally, we have this recurrence relation for number of substrings. If you have a W where all the characters are distinct, where all the characters are distinct, AI is different from AJ, where all the characters are distinct, then what is fn? Fn is number of substrings. Number of substrings of W. What is fn? That is equal to fn minus 1. That is equal to fn minus 1 plus new plus n. Tell me what are the initial conditions. For example, what is f1? What are the initial conditions? F1 is 2. F1 is 2. F1, that is 2. This is because of empty string. Okay, F1 is 2. And how many F0? There is only 1. So these are the initial conditions. Agree or not? So tell me what will be F2? What is going to be F2? F2 will be Fn minus 1 plus n. So that will be, I can say that will be like F1 plus 2. So that will be F1 plus 2. That will be 4. That is going to be 4. Agree? So tell me what is F3? What is F3? F3 will be what? F3 will be F2 plus 3. F2 plus 3. So that will be 7. Okay, very simple. Now you can also, what you can do, now you can just open it. This recurrence relation you got for the number of substrings. If you have W where all the characters are distinct, this is very important. Agree with me? That all the characters are distinct. This was important point. That all the characters are distinct. All the characters are distinct. This is important point. Okay, here. Now, here what is Fn? Fn is Fn minus 1 plus n. Now you can open it. Remember what is Fn? You already know what is Fn. What is Fn? That is number of substrings of W. Number of substrings of W. Okay, so you tell me. Now, in this case, you can open this Fn. If I open this Fn, what I will get? Tell me. I can write this Fn like this. This Fn minus 1. I can write like this. I can say that is Fn minus 2 plus n minus 1. Okay, so you can just open it. You will get Fn minus 2 plus n minus 1 plus n minus 1. And already there is n. And so on. You can just keep opening it. If you open this Fn minus 2, then what you will get? You will get Fn minus 3 plus n minus 2. Already there is n minus 1. Already there is n. If you keep opening this, then ultimately you will get something like, I can say, for example, ultimately you will get F0. Okay, ultimately you are going to get F0 plus 1 plus 2 plus and so on n. This is what you are going to get ultimately. Okay, what is F0? Tell me what is F0? F0 means zero length substring. F0 means, so that is only 1. That is only 1. Okay, so now you can calculate the answer. So what will be Fn? Fn, that will be 1 plus this sequence you got. You got this sequence 1 plus 2 plus and so on. So your answer will be 1 plus n plus 1 by 2. Okay, so this is your method number 2 for this question. For this question, the method number 2 we have seen. Is this point clear? Please tell me. Okay, the summation of this equation, that will be n plus 1 by 2. Is this clear to everyone? So this question has come in the GATE exam 3 times. You can check it out. This question has come in the GATE exam 3 times. So what will be the answer here? That will be n plus 1 by 2 plus 1. Okay, this additional one for empty string. This is for empty string, for empty string. Okay. What about this question? The question is asking non-zero lengths. So if I ask you non-zero lengths, non-zero means non-empty substrings. If I ask you non-zero lengths, then the answer will be this, yes or no? If I ask you non-zero lengths, then the answer will be this, agree or not? Because I am saying that non-zero length, the length must be non-zero. The length must be non-zero. So you cannot count this empty string. This empty string has length equal to 0. Okay, so in this case, the answer will be n plus 1 by 2. And in this question, in GATE 1994 question, he is saying all length inclusive. The question is saying all length inclusive. So actually the answer should be what? Actually the answer should be what? Actually the answer is this. Remember, this is the correct answer. Please understand. Please understand, this is actually the correct answer. This is actually the correct answer. But in the options, what option you will select? In the options, plus 1 is not given. Means the question maker is not thinking about empty string. The question maker is not thinking about null string. Okay, there are some mathematicians, they don't think about empty strings. Is this point clear? Like theory of computation people. This theory of computation people, the computer scientist, the computer science people, they will think about empty string. They think about empty string. But mathematicians, many mathematicians, they do not consider it. Okay, so here also the question maker is not thinking about empty string. So tell me which option you will select in the exam. The correct answer is actually, this is the correct answer, but which option you will select? Yes, in the exam you will select this option. This is the, I can say, best option in all of them. This is the best option. So you will select option D. So this is your question. The same question has come in the GATE exam 3 times. And we have also seen the recurrence relation. So we have seen 2 methods for solving this question. You can solve this question by 2 ways. We have seen both of them. Okay, is this clear? Please tell me. Now let's move on. Tell me the answer for this question number 5. Let Fn be the number of subsets of a set of n elements. Write recurrence relation for this. Means how many subsets are there? So you tell me, if you have a set with n elements, if you have this set 1, 2, 3 and so on, if you have a set with n elements, how many subsets are there? How many subsets are there? This Fn, this is the number of subsets. This is the number of subsets. So tell me how many subsets are there for this set S? How many subsets are there? That will be 2 power n, that we already know. That is 2 power n, because when you create a subset, then every element has 2 choices. Agree? When you are creating a subset, then every element has 2 choices. Either you can take it or you don't take it. Either you can take it or don't take it. Either you can take it or don't take it. So every element has 2 choices when you create a subset. So the answer will be 2 power n subsets are there. Now the question is asking for recurrence relation. For recurrence relation. So let's write the recurrence relation. That is also very simple. So see, what is Fn? That is a number of subsets of S. Number of subsets of S means number of subsets of n elements. So I can say number of subsets of S, whatever. Now you tell me, how can I write the recurrence relation? See, the recurrence relation I can very easily write. Just focus on this element. Focus on one of these elements. Whatever element you want, you can focus. So just focus on this element. Now you tell me, for this element, what I can do? There are 2 ways. For this element, there are 2 ways. What I can do? Either I can take it or I don't take it. See, what I can do? There are 2 ways. For this element, just focus on this element. Either I take it, this n, this element n. Either I take it, means I put it in the subset. I include this in the subset. I create a subset. In that subset, I include. Or I don't include. Or I don't include. Or I don't include. Means this n, either I take or I don't take. There are 2 choices. Now you tell me one thing. You tell me one thing. If I have already taken and here I did not take, are these disjoint? Are these 2 cases disjoint? This case and this case, are they disjoint? Are they mutually exclusive? This case and this case? Yes, because here I am taking n and here I am not taking n. So they are different. They are definitely different. So very simple. If I already take n, if I already have taken n, means this element n I have already taken. Now what I can do? For the remaining elements, I can create subset. Agree or not? Agree with me? I have already taken n. I have already taken n. This n I have already taken here. For the remaining elements, what I can do? I can create a subset. I can create a subset using the remaining elements. Agree? Is this point clear? I have already taken n. This n I have already taken. This n I have already put in my subset. So this n is already there in my subset. Now for the remaining elements, from the remaining elements, I can create a subset. I can create a subset from the remaining elements. Now, what is another point? See, if I don't take n, this n I've already rejected. Okay, this n I've already rejected. Now, from the remaining elements, I can create a subset. I can create a subset from the remaining elements. From the remaining elements, I can create a subset. Okay, so I can create a subset from the remaining elements. Very simple. Here I can create a subset from remaining elements. Subset from remaining. Here I can create a subset from remaining. Here also I can create a subset from remaining. Is this point clear? Isn't it simple? So very simple, I'm saying just focus on this particular element. Focus on this element n. Focus on this element n. Either you will take it or you will not take it. If I take it, then from the remaining elements, I will create the subset. Okay. And if I don't take it, then also from the remaining elements, I will create subset. So your answer will be what? Your answer will be what? Fn equal to, if I take n, then from the remaining elements, I will create subset. And if I don't take n, then also from the remaining elements, I will create subset. So your recurrence relation will be what? That will be Fn equal to 2Fn minus 1. Please tell me, did you understand this? Means you just take a particular element, just take any particular element. You can take any particular element and you can create two cases. Two cases you can create. Take any particular element and create two cases. Either you take this particular element or you don't take this particular element in your subset. So very simple. So if I include this n in my subset, then from the remaining elements, I will create a subset. If I don't include this n in my subset, then also from the remaining elements, I will create a subset. So my answer will be what? Fn equal to 2 into Fn minus 1. Now you can solve it. You can open it. So let's open it. Tell me what you will get. If you open it, what you will get? This 2 is already there. This 2 is already there. If I open this, what I will get? I will get 2 into Fn minus 2. Yes or no? Yes or no? Then what I can do? Then I can open it. 2 into, I can open it. If I open it, then I will get 2 into Fn minus 3 and so on. And so on. If I do like this, then what I will get? Ultimately, I will get somewhere I will get what? I will get F1. I will get F1. And when I get F1, see, when I'm getting Fn minus 3, how many 2s I'm getting? Tell me. When I'm getting Fn minus 3, how many 2s I'm getting? I'm getting total 3 2s. Yes or no? And ultimately, when I get F0, F0 means n minus n. F0 means n minus n. Okay, ultimately, when I get F0, if I'm getting n minus 3, I'm getting 3 2s. If I'm getting n minus 2, I'm getting 2 2s. So if I'm getting n minus n, then how many 2s I will get? I will get 2 power n. I will get 2 power n. Very simple. So your answer will be what? And what is F0? What is F0? Means this is the number of subsets of empty set. F0, that is the number of subsets of empty set. Remember what is F0? F0 is number of subsets of empty set. Number of subsets of empty set. Set with 0 elements. Empty set means set with 0 elements. This is your set with 0 elements. 0 number of elements. So what is the number of subsets? Tell me. For this empty set, how many subsets you can create? For this empty set, the number of subsets, what is that? Only one subset you can create, that is empty set itself. Number of subsets will be 1, and that is empty set itself. So you can see, ultimately I can say this f0 that is equal to 1. So your final answer will be what? Fn equal to 2 power n. This method, did you find interesting? See, you already know the answer, that answer is 2 power n. You already know the answer is 2 power n. But did you find this recurrence relation interesting? That you can write recurrence relation also. You can solve the same question recursively. This same question you can solve recursively. Number of subset. The same question you can solve recursively. You can write a recurrence relation and then you can solve the recurrence relation and you will get your answer. Ultimately, you are getting the same answer 2 power n. Please tell me, did you understand? Okay, let's solve this question. The next one. Let's see this. This is your Kenneth Rosen extra examples. Let me tell you, this question you will not find in the Kenneth Rosen book. Okay, if you check the book, whatever edition you check, okay, 7th edition, 8th edition, 6th edition, whatever edition you check, this question you will not find in the Kenneth Rosen book, because these are extra examples which are available on the internet. Okay, this Kenneth Rosen has a website. Okay, there is a website for Kenneth Rosen. In that website, these extra examples are available. So I have taken this question from that website, Kenneth Rosen website, extra examples. You can see. Okay, and this question is all this PDF. These extra example PDF are already available on the Washington University website. So you can see this question I have taken from Washington University. Okay, let's solve it. So what the answer for this question? The question is saying, write a recurrence relation for the number of strings of letters of ordinary alphabet. What is ordinary alphabet? Tell me, which alphabet the question is talking about? Which alphabet the question is talking about? This question is talking about English alphabet. Okay, question is simply talking about English alphabet. The question is actually talking about English alphabet. Okay, so very simple. Now, let's see the next. So the question is saying that write a recurrence relation for number of strings of letters of ordinary alphabet that do not have adjacent vowels. You do not have adjacent vowels. Okay, we should not have adjacent vowels. So remember, very simple. Let's assume that Fn. Okay, let's assume Fn. What is Fn? That is what? Fn is number of, this is number of strings. This is number of strings of length n. Of length n. Okay, let's assume what is Fn? See, Fn is number of strings of length n without, okay, without consecutive vowels. Okay, not having consecutive vowels, without consecutive vowels. So this is the Fn. Okay, now what I'm going to do, see, I'm going to call them good strings because these are the desired strings. Agree with me? Is this point clear? See, my desired strings. What are my desired strings? Just tell me this point. What are desired strings? What are desired strings? What are the desired strings? These strings of length n which have no consecutive vowels. Okay, which have no consecutive vowels. So I can say these are the desired strings. Strings of length n. My desired strings. These are, I can say, strings with no consecutive vowel. Strings with no consecutive vowels. With no adjacent vowels. Okay, these are the desired strings. Let me call them good strings. Okay, so that I don't have to. So I will simply call them good strings. Agree? I need to count all the good strings. I will simply call them good strings. I am calling them good strings. This is the word I am using. Good strings means all the strings which do not have consecutive vowels. I am using this word good string so that I don't have to repeat this long statement again and again. I don't want to repeat this long statement again and again. So I will just simply call it good string. Now tell me what we need to do. We need to count good strings of length n. What is our task? What is our task? Our task is count good strings of length n, right? Count good strings of length n. Agree with me? So far, agree with me? Count good strings of length n. We want to count good strings of length n. This is what we want to count. Okay. Remember, strings with no consecutive vowels. Strings with no consecutive vowels. Strings with no consecutive vowels. This is a good string. Okay, and the question is asking to count these good strings. So our task is count good strings of length n. Now good strings of length n, the number of good strings of length n, that is fn. This fn, what is that? That is number of good strings of length n. What is fn? That is number of good strings of length n. Number of good strings of length n. Okay, is this point clear? So very simple. I can say fn, these are number of good strings of length n. I want to count number of good strings of length n. So just focus on the good strings. Is this point clear? I want to count how many good strings of length n are there. Okay, so just focus on the good strings. So let's assume these are the good strings. These are the good strings. Now I want to count these good strings. Now in these good strings, what you have? You have those strings which end with consonant. Agree with me? In these good strings, just focus on good strings. I want to count good strings. My target is to count good strings. Okay. So these are the good strings. In these good strings, you have those which end with consonant. Agree with me? You have those which end with consonant. Which end with consonant. Yes or no? You have those which end with consonant. Which end with consonant. And you also have those which end with vowel. Okay, in the good strings, just focus on the good strings. In the good strings, we have those which end with consonant. We also have those which end with vowel. Okay, only two cases are possible. Can I say? Can I say only these two cases are possible? Either you can end with consonant or you can end with vowel. Either you can end with consonant or you can end with vowel. These are the only two possibilities. Agree? So what I will do? I will just add my fn, number of good strings of length n. This is the number of good strings of length n. That will be equal to how many this type of good strings are there where you have consonant here. Where you have consonant here. How many this type of good strings are there plus how many this type of good strings are there where you have vowel here. So this is my answer. Is this point clear? How many this type of good strings are there where the last symbol is consonant, and how many this type of good strings are there where the last symbol is vowel. Okay, so you tell me fn, this is the number of good strings. This is the number of good strings of length n. Good string means no consecutive vowels. Good string, that simply means no consecutive vowels. No consecutive vowels. Okay, I want to count. So what I can do? I can say if your good string is ending with consonant. Okay, just focus on the good strings, nothing else. Just focus on the good strings. Now, if your good string is ending with vowel, then how many? If I'm ending with consonant, let's assume here I have some consonant. Now you tell me, if there is some consonant, will this consonant create any problem to the good string? Tell me, simple point I'm asking. If the last symbol is consonant, will this consonant create any problem to the good string? No, there is no problem. There is no problem. So what I will make sure, I need to make sure that this part is also good. Agree with me? The last symbol is already consonant. I don't care about consonant. I do not care about consonant. Okay. Okay, so this consonant will not create any problem. I need to make sure that this part is also good. Agree with me? I need to make sure that this part is also good. In this part, there is no consecutive vowel. Very simple. In this part, I have no consecutive vowel. I need to make sure this part is good string. This n-1 length, this is good string. So I will count fn-1. Means good strings of length n-1. You must have good string of length n-1. Here what you must have? You must have good string. Here you must have good string of length n-1. So far agree with me? Here you must have good string of length n-1. So that is nothing but fn-1. That is your fn-1. Or what can happen? Or you can end with vowel. One more thing. See, the last symbol is consonant. How many consonants are there? The last symbol is consonant. How many consonants are there? Total 21 consonants are there. So it will be like 21 multiplied by fn-1. Okay, remember this point. When you are ending with consonant, see, if I end with B, then here I will have fn-1. if I end with B. Similarly, if I end with C, then also I will have Fn minus 1, good string of length n minus 1. If I end with D, then also I have Fn minus 1, and so on, and so on. Okay, this either this will happen, or this will happen, or this will happen, and so on. Okay, so tell me ultimately what you will get. Ultimately, what you are getting 21 Fn minus 1. Agree? You are getting 21 Fn minus 1. This is what you are getting. Because you are ending with consonant. How many consonants are there? Total 21 consonants are there. Total 21 choices are there. You are ending with consonant, total 21 choices are there. So ultimately, okay, and this part must be good. Okay, so this must be a good string of length n minus 1. So you will get 21 multiplied by Fn minus 1. Now, here you have vowel. If I have vowel here, can it create a problem? I am simply asking, if I have vowel here, can it create a problem? Yes, it can create a problem, right? So tell me, if you have vowel here, what should be here? What should be here? If you have a vowel in the last place, in the last position you have vowel. So what should be in the second last position? Remember, you just focus on the good string. You are making a good string. I am saying you are focusing on the good string. You are focusing on good string. Good string means no conjugative vowel. No conjugative vowel. So if the last position is vowel, then the second last position cannot be vowel. Vowel, that is the problem. That is not good. Okay, vowel, that is not good string. That is not good string. I am focusing on good string. My complete focus is on good string. My complete focus is on the good string. I want to count the number of good strings. So very simple point, I am saying that it must be a consonant. It must be a consonant. Now, once you have consonant here, now can I say this, the remaining part must be good? Now can I say this remaining part must be good? This remaining part must be good? Yes or no? Now can I say this remaining part must be a good string of length n minus 2? Good string of length n minus 2. This remaining part must be good string of length n minus 2. I hope this point is clear. Okay, so this is the final point. Just focus on the good string. I want to count the good string. This is what I want to count. In the good string, there are two cases. Good string means no conjugative vowels. I want to count good string. Good string means no conjugative vowel. This is what I want to count. Now, in this, there are two cases. The case number 1 is ending with consonant. Ending with consonant. If you are ending with consonant, then this must be a good string of length n minus 1. If you are ending with consonant, then remember this must be a good. This must be a good string of length n minus 1. This must be a good string of length n minus 1. Okay, so this is the point. This must be a good string of length n minus 1. So here, number of consonants, there are 21 choices multiplied by, this must be a good string of length n minus 1. Okay, here what will happen? Here you have a vowel. Here you have vowel. How many choices? 5 choices. Yes or no? How many choices for vowel? You can have any vowel, that is 5 choices. Now you must have consonant. Now here you must have consonant. You must have consonant. 21 choices. You must have consonant. You must have. Okay, 21 choices. Now this part must be what? Now this part must be what? Tell me. This part must be what? This must be a good string of length n minus 2, right? This must be a good string. This must be a good string of length n minus 2. This must be a good string of length n minus 2. Okay, good string of length n minus 2. That is fn minus 2. So you just multiply. So your final answer will be what? Tell me. Tell me the final answer. The final answer, fn is equal to 21 fn minus 1 plus 5 multiplied by 21 multiplied by fn minus 2. Okay, this is your final answer. This is the final answer. Tell me, what are the base conditions? This is the final answer. What are the base conditions? Means how f1, how many? F1 will be what? That will be 26. F1 will be 26 because, okay, because you can put anything here. You will never have conjugative vowels. You can put anything here. You can put anything here. You will never have consecutive vowels. Consecutive vowels you will never have. What is F2? What is F2? You cannot have consecutive vowels. See, for F2, you can do like this. Either your consonant, consonant, either your consonant, consonant, or what you have? You have consonant vowel, or what you have? Your vowel consonant. Okay, so what is F2? Tell me what is F2? F2 will be like 21 multiplied by 21. This is the consonant consonant. And consonant vowel, that will be 21 multiplied by 5. And vowel consonant, that will be 5 multiplied by 21. So what is your F2? Tell me, what is your F2? What is that? That is 21 whole square plus 2 plus 210. Plus 210. Okay, you can check it out. This will be like this. So tell me what is this value? Can anyone tell me? 210 plus 21 whole square. What that will be? This value. Can you find out? This value is 651. Okay, so this is your F2. So we got F2 also we found F1 also. Now you tell me what will be F3? What will be F3? That you can find from this equation. F3 will be 21 multiplied by F2, 21 multiplied by F2 plus, don't calculate, I am just telling you that F3 will be 21 multiplied by F2 plus 5 multiplied by 21 multiplied by Fn minus 2, means F1, that is 26. So this will be your F3. So anyway, this is the question. Did you understand this question? Please tell me. This is a nice question, right? A simple question. This type of question we have already done, but this is a very nice question. I hope you understood. Okay, without consecutive vowels. Now let's move on. Okay, let's see this question. Tell me the answer for this one. This is Kenneth Rosen, exercise 8.1, question number 3. A vending machine dispensing books of stamps accepts. So there is a vending machine, and that vending machine is accepting $1 bills, $1 coins. So, okay, $1 bills, $1 note, or $1 coin, or $5 note. Okay, and what do you want? Find a recurrence relation for the number of ways to deposit and dollars. You want to deposit and dollars. In this vending machine, you want to insert and dollars such that order matters. Order in which you are inserting, okay, in which order you are inserting, that matters. Okay, that matters. So tell me what will be the answer. Now this is very easy for you. We have done a lot of practice of recurrence relation. Now this is very easy for you. So these are the choices. Either you can put $1 coin, either you can put $1 coin, or you can put $1 bill, or you can put $5 bill, or you can put $5 bill. So these are the choices that you have. Okay, and ultimately what you want Fn. Fn means number of ways to insert and dollars. This is number of ways to insert. This is the number of ways to insert and dollars in this machine. In this machine, I want to insert and dollars. Okay, so I want to insert that. So tell me, if you want to insert and dollars, what you can do? I want to insert and dollars. Then what I can do? I can start with $1 coin. Agree with me? Can I start with $1 coin? Can I start with $1 coin? Okay, if I start with $1 coin, then how much more work I need to do? If I start with, ultimately, remember, I need to insert and dollar. Ultimately, I need to insert total and dollar I need to insert. If I start with $1 coin, if I insert this $1 coin first, then how much work I need to do? Remaining, okay, I need to insert n minus $1. Agree? I need to insert n minus $1. Or what I can do? I can start with $1 bill. I can start with $1 bill. If I start with $1 bill, then I need to insert n minus $1. Then I need to insert n minus $1. Or what I can do? I can start with $5. I can start with $5 bill. If I start with $5 bill, then I need to insert n minus $5. Then I need to insert n minus $5. So your final answer will be what? The recurrence relation. The recurrence relation is that will be 2 into Fn minus 1 plus fn minus 5. Okay, so this will be your recurrence relation. Point clear? This is the recurrence relation. You can also find the conditions you can find. Okay, the initial condition you can easily find. I leave it up to you. Okay, you can do that. Okay, but the point is this is the recurrence relation. This is important. The initial condition you can find. Okay, let's move on. So you can see here, the solution is already given. If you find the initial condition, you can see here. These are the initial condition. These are given. You can read it. The solution I have already given to you. See, in this question, we need to write recurrence relation. That we have done. This recurrence relation we have already done. Now, you need to find the initial condition. Also, you need to find what is F10, number of ways to deposit $10. So that solution is already given here. You can pause the video and you can watch it. Okay, you can check it. Now let's see the next question. This is your question number 8. Kenneth Rosen exercise 8.1, question number 10. Application of recurrence relation. Okay, this is interesting question. So tell me the answer for this one. What the question is saying? The question is saying that find the recurrence relation. You need to find the recurrence relation for number of bit strings that contain 0, 1. Containing 0, 1. Okay, you must contain 0, 1. This is the question. You must contain 0, 1. Okay, so containing 0, 1. You remember? So let's assume that what is Fn? Fn is number of bit strings. This is the number of bit strings of length n. Of length n containing 0, 1. Okay, you must contain 0, 1. You must contain 0, 1. Okay, containing 0, 1. So very simple. This is your Fn. Fn is number of bit strings of length n containing 0, 1. We must contain 0, 1. Okay, so first you find the initial conditions. First you tell me what will be F1. Can you contain 0, 1? If you have only one length, can you contain 0, 1? You cannot contain 0, 1. You cannot contain 0, 1. If you have two length, then containing 0, 1, how many you can create? Containing 0, 1. Only one you can create. Only one you can create. Okay, what will be F3? F3 is like this. See, F3 is like this. Containing 0, 1. If you want to contain 0, 1, tell me simple point I'm asking. Simple point. If I put 0, 1 here, can I say anything I can put here? If I put 0, 1 here, my task is done. What I wanted to do, that is over. My task is over. What I want to do, that is over. I want to contain 0, 1. Already there is 0, 1. My task is over. So I can put anything here. I can put anything here. So there are two ways. Okay, or what I can do, if I put 0, 1 here, then what I can do, I can put anything here. Then I can put anything here. So F3 will be 4. Agree or not? F3 will be what? That will be 4. Is this point clear? Initial conditions, are they clear for this question? Now let's see. Now let's see the recurrence relation. So this recurrence relation is also very interesting. So you tell me, if you are, I want to find number of bit strings of length n which contain 0, 1. My complete focus is on the 0, 1. What I want, tell me, I want 0, 1. Okay, I want 0, 1. My complete focus will be on 0, 1. I want this 0, 1. So tell me, what are the possibilities? The possibilities are these. I want to count this Fn, I want to count. So what are the possibilities? The possibilities are these: n length bit strings. Okay, or I can say, let's call them good strings. Containing, what are the good strings? Let me define. Please see. Let me define good string. What is good string? A string containing 0, 1. Okay, is this point clear? A string containing 0, 1. A string containing 0, 1. A string containing 0, 1, that is a good string. Okay, is this clear? A string containing 0, 1, that is a good string. So what is my task? Tell me, what is my task? A string containing 0, 1 is a good string. What is my task? My task is how many length n good strings are there. Okay, my task is count the number of length n good strings. Length n good strings. Okay, very simple. Good string means a string containing 0, 1. Now you completely focus on good strings. N length good strings. Just focus on N length good strings. Only focus on this. Okay, completely focus on N length good strings. This is what I want to count. I want to count N length good strings. These are the N length good strings. What are the possibilities? These good strings, I want to count these good strings. Now these good strings, either they can end with 1 or they can end with 0. Agree with me? Only two cases are possible. Do you agree? Only two cases are possible. Okay, I want N length good strings. I want good string means containing 0, 1. This is good string. So tell me. Now there are only two cases possible. Either this good string will end with 1 or it will end with 0. Okay, so I will count these plus I will count these. This will be my answer. My answer will be I will count these plus I will add these. Okay, so I can say these good strings you can do like this. Either they will end with 0 or they will end with 1. Either they will end with 0 or they will end with 1. Okay, if you are ending with 0, then tell me, can it play any role in making a good string? If you are ending with 0, if you are ending with 0, can this 0 play any role in creating a good string? This 0, good string means you want to contain 0, 1. You want to contain 0, 1. You want to contain this 0, 1 substring. Contain 0, 1 substring. Now, a simple question I am asking. If you are ending with 0, can this 0 play any role in creating the good string? No, it cannot, because this is already at the end. This 0 is already at the end. This 0 is at the end. See, this 0 is at the end. So it cannot give you 0, 1. Can this 0, 1? Can this 0 give you 0, 1? Simple question. Can this 0 give you 0, 1? No, it cannot give you. So who will give you 0, 1? So it means here you must have a good string of length n minus 1. Agree with me? Here you must have good string of length n minus 1. Here you must have good string of length n minus 1. Agree? So far, is this point clear? So I am saying that if you end with 0, now this 0 cannot do anything. Okay, because you are ending with 0. So this 0 cannot give you 0, 1. This 0 cannot give you 0, 1. This 0 cannot play any role in giving you a good string. Okay, good string means a string containing 0, 1. So if the 0 cannot give you anything, then what you can do? From the remaining, in this remaining, you will search for good string of length n minus 1. In this remaining, good string of length n minus 1, that is nothing but f n minus 1, right? Okay, is this clear? Or what can happen? Or you can end with 1. Now tell me, if you are ending with 1, then what will happen? If you are ending with 1, can this 1 play any part? Simple question I am asking. Can this 1 play any part in giving you good string? Good string means containing 0, 1. So can this 1 play any role in giving you 0, 1? Yes, it can play. See, one more thing. If you are ending with 1, now, if you have 0 here, is my task over? Is my task over? If you have, see, you are ending with 1. Now, if you have 0 here, now can I go home? My task is done. I don't care about this. I already got 0, 1. 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 So my task is done. I don't care about this area. Do I care about this area? This area should be good or bad. This area should be good string or bad string. This area, just focus on this area. This area should be good string or bad string. This can be anything. This can be anything. I already got 0, 1. I already got 0, 1. I already got 0, 1. So this area can be anything. I don't care about this area. Here you can put anything you want. Here you can put anything you want. So if I'm putting anything I want, then there are 2 power n minus 2 ways. Okay, because every position has 2 ways. Every position has either I can put 0, 1 or I can put 0 or 1, 0 or 1, 0 or 1. Every position has 2 ways. So finally I can say 2 power n minus 2 ways. Now, but there is something interesting here. If I put 1 here and this symbol is also 1, now what to do? See what I'm saying. Now what to do? Now what to do? In this case, what to do? This case is pending. Okay, so Now tell me, I want n length good string. I want n length good string. Good strings means containing 0, 1. I want n length good string. Good string means containing 0, 1. Okay, there is something interesting here. See, if I'm just focusing on this case because this case is pending. Agree? Can I say? Can I say only this case is pending, right? This case is pending. This is the pending case. So in this case means when you have 1 here, you already have 1 here, and here also you have 1. Here also you have 1. Now what to do now? Anyone want to suggest what to do now? Can I simply say that, okay, a good string you find here? Can I simply say, just find the good string here? Can I simply say, find the good string here? Can I simply say that find the good string here? Is this simple? Can I say, find the good string here? Just find the good string here. Can I say that? What is wrong here? What is wrong here? Please tell me. Anyone? What is wrong here? See, this is wrong because this can play some role. Yes or no? You are putting it out of the equation. This one can play some role. Okay, are you getting my point? What is wrong here? This is wrong. I am saying that if this is 1, this is also 1. This case is pending. This case is pending when you are ending with 1, 1. When you are ending with 1, 1, this case is pending. This case is pending. Okay, now if you are ending with 1, 1, can I simply say that here you must have good string? The answer is no. This is wrong. Why this is wrong? The focus, why this is wrong? This is wrong because if I have here something like this, okay, here I have something like this, and you are ending with 1, 1. Okay, is it a good string? Is it a good string? Or in this area, just focus on this area. Just focus on this area. Is this a good string? No, this is not a good string, but overall I am getting a good string or not? Notice. Overall I am getting a good string or not? I got 0, 1. So can I say here you must have good string? Can I say? Is this correct? That I must have good string here. I must have good string here. Is that enough? Or sorry, I can say I must have good string here. That is necessary. Is that necessary? No, that is not necessary because this one can play some role. This one can play some role. Is this point clear? Please tell me. I hope this point is clear. See, I am saying that this case, when you are ending with 1, 1, this case, when you are ending with 1, 1, this case is pending. When you are ending with 1, 1, I am saying that if you say that here you must have good string, means fn minus 2. If you say here you must have good string, what I will say? I will say this is not necessary. I will say this is not necessary, not necessary, because I can have this. I can put 0, 0, 0, 0, 0. Still I will get a good string. Still I will get a good string. See, look. Still I am getting a good string. So is this point clear that this is wrong? Is this point clear that this is wrong? Did you understand that this is wrong? Okay. Now, if this is wrong, then what is another idea? Yesterday, some students suggested in the private GoClasses private Telegram group, some students suggested that, sir, in this case, what you do, you simply count fn minus 1. In this case, you simply count fn minus 1. Means here you must have good. Here you must have good. Means here you must have good. Here you must have good. Here you must have good. Is this correct? Here you must have good. Is this correct? Is this correct? That here you must have good. Please tell me. Here you must have good. Is this correct? This is also wrong. This is also wrong. Why this is wrong? Why this is wrong? This is also wrong. Why this is wrong? Why this is wrong? Because notice, already there are 2 ones. Already there are 2 ones. See, please focus. This is also wrong because the reason is this. It is not necessary, right? Okay, when you say that you have fn minus 1 in this area, when you say fn minus 1, please focus. When you say that this area has fn minus 1, this area has a good string of length n minus 1. When you say this area has good string of length n-1, are you considering this possibility? Are you considering this possibility in this area? In this area, are you counting this possibility? Please tell me. When you say that this area, focus on this area, focus on this area. When you say this area has good string of length n-1, then you are counting this, right? You are counting this. You are counting this, but that is not possible here because already it is ending with 1. Is this point clear? See what I'm saying. Please notice. In this area, look at this area. In this area, if you say fn-1, if you say good string of length n-1, then you are considering this string. Then you are considering this string, right? You are considering this string because this is also a good string of length n-1. This is also a good string of length n-1. So you are considering this string, but this string cannot go here because you are ending with 1, 1. Because this area is ending with 1. This area, just look at this area. This area is ending with 1. This area is ending with 1. So, but you are counting this. You are counting this. So that is wrong. Did you understand this point? That this is also wrong. Because here you cannot have, but you are counting it. This string in this area. Okay, in this area, this string you are counting, but this string cannot go in this area because this area is ending with 1. This area is ending with 1. I hope everything is clear. What is wrong? Did you understand? You cannot use fn-2. You cannot use fn-2. Similarly, you cannot use fn-1. So now you tell me, when you are ending with 1, so what should I do? If you are ending with 1, again, very simple. It will go. See, if you are ending with 1, then there will be 2 cases. See, if you are ending with 1, 1, if you are ending with 1, 1, you are already ending with 1, 1. You are already ending with 1, 1. Okay, when you are ending with 1, 1, there are 2 cases again. Again, here you can have 0 or here you can have 1. If you have 0, then tell me. If you have 0, how many ways? Now here you can put anything. Now here you can put 2 power n-3. And again, when you have 1 here, then again the same story will go. Agree with me? The same story will continue. Please tell me. The same story will continue. The same story is going to continue. Here you will have 2 power n-4. Here you will have 2 power n-4. And here you will have, again, here also, again, the same story will continue. Are you getting this point? Isn't this interesting? I hope you are understanding this question. See, I'm telling you, again, I'm telling you, you have fn. What is fn? This is n length good strings. Take your copy pen. This is n length good strings. Good strings means containing 0, 1. Good strings means containing 0, 1. Containing 0, 1. Okay, good string means containing 0, 1. Okay, so you want to count fn, that is n length good string. Okay, good string means containing 0, 1. So what I can do? These are the possibilities. Okay, just focus on n length good string. This n length good string. Here you have 2 ways. If you are ending with 0, okay, just tell me this point. If you are ending with 0, then you are looking, then what you will do? Then this 0 cannot play any role. Agree? If you are ending with 0, can this 0 give you 0, 1? Can this 0 play any role in good string, in giving you good string? Tell me. Good string means containing 0, 1. Good string means containing 0, 1. Simple question I'm asking, that if you end with 0, can this 0 play any role in giving you good string? Can this 0, this ending with 0, can this 0 play any role in giving you 0, 1? In giving you 0, 1? No, it cannot play any role. There is no role. There is no role. And because there is no role, no role. So what you will do? You will search for good string here. Agree? You will search for good string here. You will search for good string here. Agree? You will search for good string here. That means fn-1. Okay, very good. Very good. Or what you can do? You can end with 1. or you can end with 1. Now, when you are ending with 1, or you can end with 1. If you are ending with 1, then two cases will be there. What are the two cases? If you are ending with 1, I am ending with 1. Now, there are two cases. I am already ending with 1. Now, there are two cases. If I put 0 here, then do I care what is here? I already got 0, 1. I already got 0, 1. I already got 0, 1. So here you can give me anything. Here you can give me anything. Whatever you want, you can give me anything here. Okay, give me anything. Means here you can put anything. Means here you can put anything. So that is the reason 2 power n minus 2. Okay, but if this second place is 1, if this second place is 1, can you notice you have come back to the same situation? Can you notice you have come back to the same situation? Okay, can you notice? Because this 1 can play some role, agree? Can this 1 play some role to give you 0, 1? Can this 1 play some role to give you 0, 1? Yes, it can play. It can play some role. See, it can play some role. This 1 can play some role to give you 0, 1. So what I will do? Again, I got the same situation. I got the same situation. Again, what I will do? Again, I will do like this. I already have 1, 1. I already have 1, 1. Now, I will consider if you have 0 here. If you have 0 here, then what you will get? You will get 2 power n minus 3. Okay, you will get 2 power n minus 3 because you already got 0, 1. You already got 0, 1. But if you have 1 here, then again what will happen? Then again the same. Then the same story will continue. If you have 1, 1, then the same story will continue. The same story will continue. If you have 0 here, then you can put 2 power n minus 4. And if you have 1 here, then again same story will continue. Again same story will continue. Did you understand? Did you understand? So what I got? I got Fn equal to what? I got Fn equal to Fn minus 1. I got Fn equal to Fn minus 1 plus a series I am getting. Did you notice a series I am getting? 2 power n minus 2, 2 power n minus 3, 2 power n minus 4, and so on. A series I am getting 2 power n minus 2, 2 power n minus 3, 2 power n minus 4. Till when I will get this series? This series, when this series will end? Okay, when this will end means you are going like this. Whenever you have this 1, 1, 1, see this is happening. Whenever you have this 1, 1, 1, whenever you have this, for example, if you have 4, 1, if you have 4, 1, then again you are going like this. Then again you are going like this. You already have 1, 1. You already have 4, 1, 1. And if you have 0 here, then you can put anything here. So you will get 2 power n minus 5. Okay. But if you have 1 here, if you have 1 here, already 4 1s are there. If you have another 1 here, if you have another 1 here, if you have another 1 here, then again you will go. Then again you will go. Okay. Then again you will go. Here you will get 2 n minus 6. But then again you will go. From here again you will go. Then you will get 2 n power n minus 7. But then here again you will go. When you will stop? When this branch will stop? Tell me. You are going like this, but ultimately when this, okay, you are going like this means 2 power n minus 7, 2 power n minus 7, and you are going like this. But when this branch will stop? Tell me. This branch will stop when ultimately you get all ones. Ultimately, because you cannot get all ones because you want a good string. This branch will stop when you get all ones. When you get all ones, and in this position, only one position is there. Only one position is there, and in that position you put 0. Okay, are you getting my point? This branch will stop when you have all ones. Only one position is remaining. Only first position remaining. First position. This is the first position. This is the first position. In this situation, you will stop and you will simply say that 0 must come. In this situation, you will stop and you will say that yes, 0 must come. All the remaining are ones. Okay, and there will be nothing here. There will be nothing here. There will be nothing here. Please tell me, did you understand? So ultimately, you will stop at 1. There is only one way. Okay, so this recursion will stop at 1. This will just keep going like this, or I can say, okay, you are decreasing. Ultimately, you will go till 2 power 0. Please tell me, did you understand this question? Anyone here who understood this question? What is happening here? I told you everything. See, I told you what was the mistake. I told you that if you do this, what is the mistake? See, I told you fn equal to fn minus 1 plus fn minus 2. I told you there is a mistake here. See, if you remember, please remember what I told you. What did I tell you? I told you that this is wrong. I told you this is wrong. And why this is wrong, I told you. Agree? See, this is wrong. And why this is wrong, I told you. Why this is wrong, we have seen. We have seen why this is wrong. Yes or no? Is this point clear? Similarly, I told you this is also wrong. Fn minus 1 plus 2 power n minus 2 plus fn minus 1. I told you this is also wrong. Agree? This is also wrong. This is also wrong. I told you why this is wrong. We have seen. We have seen. So ultimately, what is correct then? Ultimately, what is correct then? Ultimately, this is correct. Fn minus 1 plus a series you will get. You will get a series 2 power n minus 2 plus 2 power n minus 3 decreasing, 2 power n minus 4 decreasing 2 power 0. Okay, is this point clear? This is correct. This is correct. This series you are getting, and this is correct. Please tell me, did you understand? Did you find this question very interesting question? In the GATE exam, this question can come. Already in the GATE exam, there are 5 questions on recurrence relations. In the GATE exam, we have seen all the GATE exam questions, right? In our recurrence relation playlist on the Go Classes YouTube channel, we have seen all the GATE exam questions. You can see in the GATE exam, they are asking this type of questions. In the GATE exam, they can ask you this type of question. Writing recurrence relation. There are 5 questions in the GATE exam. They can ask you this type of question. Did you find this question something interesting, something new? Something new is happening. Okay, and remember the complete analysis I am telling you. I am telling you why this is wrong. I told you why this is wrong. And I also told you why this is wrong. Why this is wrong. Ultimately, the correct answer is this. So what is the final answer? If you see this series, what is the series? 2 power 0 plus 2 power 1 plus 2 power 2, 2 power n minus 2. What is this? This is GP. This is what? This is your GP. How many terms? GP with how many terms are there? 0 to n minus 2. How many terms are there? There are total n minus 1 terms. Okay. How many terms are there? Total n minus 1 terms are there. So tell me, what is the summation? The summation is first term multiplied by common ratio power number of terms minus 1 divided by common ratio minus 1. So that is 2 power n minus 1 minus 1. So your final answer will be what? Tell me your final answer. That will be fn minus 1 plus. That will be fn minus 1 plus 2 power n minus 1 minus 1. This is the final answer. This is the final answer. Tell me, understood? Did you understand this? Please tell me a simple point. Did you understand this? This analysis, did you understand? Let me know. Please tell me. Did you understand this analysis? So this is your final answer that we got. Okay, initial condition we have already seen. This is the recurrence relation that we will get. And this, what is this? This is the number of n length bit strings, n length bit strings containing 0, 1. Containing 0, 1. Okay, so this is the analysis. This is the complete analysis of this question. I hope you understood. Very simple, but very interesting. Okay, the most interesting part is actually finding the mistake. Why this is wrong? Finding the mistake. Similarly, why this is wrong? Finding the mistake. Finding the mistake is also very interesting. Okay. So anyway, this is the complete analysis of this question. I hope you understood. So this was your question. Find the recurrence relation. So your answer will be Fn is equal to Fn minus 1 plus 2 power n minus 1 minus 1. This is your final answer. Okay. So I think that is enough for today. The remaining questions we will continue tomorrow. Okay. So there are some more beautiful questions are there. For example, this question we will do tomorrow. Do not contain 3 consecutive 0. You can try this. This type of questions we have already done in our recurrence relation playlist. Some more questions we have done today, and the remaining questions we will solve tomorrow. Okay. Is that clear? I think that is enough for today. Whatever we have seen today, that is enough. Please tell me, did you understand in this session? Did you understand something new? Some new things did you understand? Some new questions we have seen, some new problems we have seen. Okay. Some interesting questions. Now, the remaining questions we will solve tomorrow. Okay. So thank you, everyone. See you tomorrow.